All right, well, before we continue on with our performance metrics topic, I do want to go back and visit something that I was a little bit stumped with the other day, last time. A really good question was, why don't we analyze the heap sort by writing down the recurrence and then solving the recurrence? And if you will recall, the recurrence for the heap sort was this. T of n is big theta of 1 in the base case, and it's T of n minus 1 plus big theta of log n in the other case. So this is for n less than or equal to 1, and this is for n greater than 1. And I was about to go write up a little exercise for the back of the book that had an example of a recurrence that had this form in it with some numbers in it, and to prove that it was, and to prove that T of n is n log n is a solution of this. Turns out to not be easy at all. Now, check this out. First of all, the master method does not work. I don't know if you remember the master method. We didn't require it, but the master method only works for recurrences that have the form T of n divided by a constant. Are you with me? So the master method is automatically out for this.
Divided by 1.
So the master method is out, and here's the other problem. And it's also very difficult to come up with a problem where you can prove a solution by guessing the solution and then proving that it is. And why is that? The reason for that is because this is T of n minus 1, right? T of n, oh yeah, actually it would be this, wouldn't it? It would be prove that it's true for T of n plus 1, assuming that it's true for T of n. Isn't that how we would do it? So we would, so the way we would do it is we would say prove T of n plus 1 equals blah 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 is the solution, assuming what? Assuming T of n equals blah 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 as the what?
Inductive hypothesis.
As the inductive hypothesis. Right? That's how we would do it. Are you with me? And so what would you start with? You start with T of n plus 1, right? Because this, you have to prove that this equals this. So you would start with this, right? And you would say T, and then equals by the what?
Oh.
You would say equals by T of n, and then this would be T of n plus 1 minus 1, so that would be T of n. Are you with me?
Yeah.
But look, this would be big theta of what? Now watch this, you guys. This would be big theta of what? If you said prove T of n plus 1, this would be big theta of log what? N plus 1. What is the log of a sum? No. The log of A times B is the log of A plus the log of B. But what is the log of A plus B?
We don't know.
There is none. There is no closed form solution for that relationship. The log of the sum, you can't manipulate that. There's no closed form solution for what it is. You understand what I'm saying? See, look, we know that the log of A times B is what? The log of A plus the log of B, right? But if you say log of A plus B, that's big fat question mark. There's no way to Google that. See what the log of the sum is. You can do expansions, Taylor series, blah blah blah, and all that. But there's no. It's not. So it's very. I thought I could come up with a little, set this up and prove that this is the solution. But no, it's quite difficult. So anyway, that was a little note because you had asked, why don't we write down the recurrence and prove that the recurrence, and the answer is it's very difficult to do that. So anyway, so we put that one to bed. Okay, so now, then, at the end of class last time, we were talking about performance metrics and the fact that now that we have all this theory, remember here we had this theory. Here's this list of the theoretical asymptotic bounds of the sort algorithms, and we have gone through all of these. So these you need to know backward and forward. Okay. And now the question is, now how do we know, this is the theory, but what about the practice? And the practice would be, our objective now is to do a project where we actually compare, where we actually measure how fast these algorithms execute and compare them with what the theory is. Does everybody see that's the deal? And we said, now why couldn't you just, to time a program, why couldn't you just use a stopwatch? Human response, okay, but on the other hand, isn't there a system clock? Couldn't you just check the system clock? How about this? Suppose, you can access the system clock and you can find out, what the time is in milliseconds when it starts, and then when it stops, check the time. And just subtract. So what's wrong with, why couldn't you do that?
I don't know.
Do you know why you couldn't? Do you know some of the problems with doing it that way? Can you think of some problems of why that would?
Count also accessing the clock?
Well, accessing the clock is very, very short.
Well, but and that would be the same for all of them, so like we would add them.
Yeah, but there's another very important reason why that wouldn't work either.
Are people's clocks off?
No, clocks are fine. Clocks are accurate. What's happening in your computer is only your program. When your program executes, is it only your program executing all by itself? It's not. You might be streaming some music, watching in the background, blah, blah, blah. And what's your computer doing? It starts your program, then it swaps it out, it computes for a little bit, and then you get the next note of your song and plays that, and then puts your job back in and starts it. So all these jobs are being swapped in and out all the time. So just because you know what time it started and what time it ended, all that time in between was being spent on other programs. A lot of it was. Now, does everybody understand that? So even that doesn't work. Now, how could you mitigate that? How could you
Count the number of.
Yeah, and that's what we were saying at the end of class last time is what we need is a way to actually do a statement execution count. But there is one other thing we should say about statement execution counts that you really should know about. And that is, suppose we have a loop, and inside the loop we have if x is less than something like max limit, and then down here we do x plus plus. And when we did a statement execution count, we counted this once, and if this executed, we counted it, and then if this executed, we counted it, and then we just added up those statement Now, do you see there's actually a problem with this, with doing it that way? Can you see why that is? There's even an inaccuracy there. Yeah.
Is it because for loops we only count it once, and it includes the increment?
Well, that's a good point. Like in that for loop, we would have 3 different things.
Yeah.
And one of them was an assignment, and one of them was a compare. So yeah, that is a complication. So one statement at C++ is more than one statement at assembly language or machine language. That is one really important difference. And there's a second equally important difference. It is that one kind of statement takes longer to execute than a different kind of statement, more cycles. And so to be really accurate, what would you have to do?
You have one variable for each type of count?
Yes, you would have, well, what you would do is you could look up in the manual and see how many cycles it takes each statement to execute, and then to get the actual time, you would have to multiply
that's what you have
this
variables.
by the time, right. So you would have to wait. Instead of adding, instead of being a sum, it would be a weighted sum. So like if you had statement 5, statement 6, statement 7, and if this executed n times, and this executed n minus 1 times, and this executed n minus 1 times, you wouldn't just add this plus this plus this. You would add this you would add this times the cost. You know, like, let me just make up some numbers. Suppose this one took 3 cycles to execute, and this one took 5 cycles to execute, and this one took 1 cycle to execute. Then you would do this times this, plus this times this, plus this times this. And these would be the costs. This is called the cost of executing. And that's how you could get it actually in seconds. Do you see, does everybody see what we're saying? That would be the way to do it more accurately. And you know, sometimes you do that. Sometimes software developers, software engineers do this for estimating times. You know, it's a weighted sum. Is everybody following this all right? Okay, yeah, question?
So like the ends are like what we would calculate from?
Yeah, how many times this statement executes, but if it takes 3 cycles for each one of these, then it's 3 times n cycles for here. And if it takes 5 cycles for these, then it's n minus 1 times 5. That's how many cycles it took to execute this one. You see? And these, these could be these are called the costs. And so it would be, instead of being a sum, n plus n minus 1 plus n minus 1, it would be a weighted sum, n times 3 plus n minus 1 times 5 plus n minus 1 times 1. So it would be a weighted sum, where each one has a cost. That's an important concept, actually. And that's, if we were doing this more precisely, we don't have time to go do all these refinements, but that's the way it would have to be done to do it accurately. And so what we're going to do is, we are going to have a way to not, it would be nice if we had a way to count every single statement in our algorithm, but instead of being able to count every single statement, what we said last time is, instead of being able, it would be difficult to count every single statement that gets executed. Some research, you know, in performance research, sometimes they do that. But for our purposes, we're going to be a little less ambitious. So what we said last time is that we had 3 possible metrics: the number of array element comparisons, the number of array element assignments, and the number of array element probes. And we illustrated that with this. We said that if a sub I is less than a sub child, what we are doing is we are comparing 2 elements of an array in a sort. And then what was the sub I and the sub child? What were those called? Do you remember? Those are called probes. So we had this one statement also we would have a way to count that it probed the array twice when this statement is executed. And then the third one is we're going to have a way to be able to count whenever you make an assignment to an element of an array. So that's one element assignment. And I think that's where we ended last time. What we're going to do now is there are 2 decorator patterns that we are going to use to collect data. And there is, the first one is called Parametric Decoration. And the Parametric Decoration is for the comparison and the assignment metrics. And really, the parametric decoration is really not one of the gang of 4 object-oriented design patterns, because it doesn't involve inheritance and setting up an inheritance. So it's really not an object-oriented thing. Okay, it's called parametric decoration. And the second one is called the decorator design pattern. And this one is one of the design patterns that is in the Gamma book. The decorator design pattern. And the decorator design pattern is used for the probe metric. Now, what we're going to do now is we're going to demo a project that you need to install in your, on your DP4, from your DP4DS distribution, and where I'm going to demo how these counts, how to actually take the data to do these counts. And let me say that this is in preparation for a paper that you're going to write, and you're going to take the data using this project and then analyze the data and compare it with the theoretical expectation. Okay, so let's do the demo. Okay, so here's our demo. Now if we scroll down here, we will see in the projects pane, check this out. We have this one here is called sort comp assign. And what do you suppose that is? Why do we call it sort comp assign? And what is this one? Why do we call this one sort probe?
So like how many target openings?
Well, this project collects data on comparisons and assignments, and this one collects data on probes. Are you with me? So watch. So here, if we go to the files part here, and we take a look at the sort comp assign, and we see, now look what we have here. We have these 6,400, and why do you suppose we call this D? Here, let's look at this one. Because now instead of being integers, what are they? They're doubles. But see, isn't it fortunate that we are using C++ templates, because we can sort integers or we can sort doubles. All right, so let's go back to projects, and let's run the sort comp assign. So here we'll run it. Okay, so here's our run. So enter array capacity. So let's say 50. And let's say D0050. Boom, and look what it did. Now look, let's scroll up here. First thing that it did is that it printed out the 50 numbers from the file, and now look what it does. It says insertion sort ... initial performance count, and it has an assignment count and a comparison count. So we see that these counts start off at 0. Are you with me? Then what it does, oh, look at what it did here. Sorted post condition satisfied. What do you suppose the program actually does? It goes through and does what? Checks the post condition to make sure that it's sorted. And how does it do that? It has to do it in a what? In a loop. So it just starts with the first one, the second, makes sure the first one is less than equal to the second one is less than equal to the third one, and it goes boom. So now you don't have to visually verify it. You can just see the printout here. So when you get those big old long files, you don't have to visually, so it tests the post condition. And then what does it do? Final performance count, assignment count, 652, comparison count, 651. So this says that the insertion sort, this is how many assignments were made, element assignments were made in the insertion sort. And this is how many element comparisons were made in the insertion sort. And then it says selection sort. So we verify that the counts are reset to 0. Are you with me? Then it says sorted post condition satisfied, so it does the selection sort, sorted post condition satisfied. And look, ooh, look at this. 147 assignments, but what? 1,274 comparisons. Taking the data for us. Yeah? Merge sort. We initialize the counters. Assignment count 572, comparison count 272. Here's the quick sort, and let's see, did we have the heap sort? Yeah, heap sort here, and then the quick sort. So did we do all 5 of them? What was it? It was insertion, selection, merge, heap, and quick. Right? And it took data on all those. And here, you could actually do the same thing with the sort probe. So here, if we run sort probe, enter array capacity, so this is, let's do 50 again. And let's do D0050. And see, there's this time our probe, it probes how many. So what was the probe? How many times you do sub, that's when it probes it, the subscript. All right? Okay? So now here we can take a look at, I think it might be a little instructive to take a look at the comp assign. Let's look at the main program. I don't have slides for this, but I think it might be nice to see what the main program looks like. See what it does? We have an insert sorter, a select sorter, a merge sorter, a quick sorter, and a heap sorter, right? And then I just run through each one. Okay, so you get the read count and the array data, and then we have we get a new insert sorter, and then I call this little test sort, which is down here at the bottom. And this test sort takes the sorter and it does all this stuff. And look, here's the post condition. Sorter, arrow, sort, temp array, 0, length -1. And for int I gets 1, I less than length, I plus plus. If temp sort array is greater than, then sorted gets false. So it goes through and tests them all to make sure that each one is less than or equal to. And then if sorted, precondition satisfied, else post condition not satisfied. See? So there, that's all done for us. And that is the end of the demo. Okay, so that's the problem that that's the project that you're going to use to collect your data for your paper, okay? And so you'll want to install that next chance you get. And now what we're going to do is we're going to go through a code walkthrough to show how this program works, the ideas behind it. Now, keep in mind, this is quite amazing. What we're going to do is this uses the abstract sorter, the A sorter. It uses the code that you already have written. So it's actually going to use your code. So you don't have to modify your code at all. You see what I mean? And I tell you, years ago, when I wanted to have students take performance data, I used to have them go in and put little counters, inside their code, like have a variable and start it to 0, and each time it does this, do plus plus, and then you see, in other words, it used to be, if we didn't have this object-oriented design, this parametric design pattern, you'd have to go in there and modify your code in order to do the count. Do you see what I mean? But the beauty of this is that you don't have to modify your sort code. So how in the world does that happen? How can we have that happen? How can it actually run your program without modifying your program and yet count how many times these particular statements execute? It's really clever. This is really a very slick idea. So watch how this works. So first of all, let's start with figure 4.30. Figure 4.30 shows so we have a separate class called a counter. All right. And this counter has, so what does a counter have? A counter has a delta, which is an int, and a count, which is an int. Now you see that delta? That delta represents the cost that we were talking about. Do you see what I mean? So we set up these counters to be general. So if you wanted to assign a cost to each count, you could. Now in our projects, we're just going to keep it simple, and the delta will always be just 1. So when we said you could take this kind of a statement and have it cost this much, and another kind of statement have it cost this much. Well, our costs, so that delta is the cost. Okay. So every class has a delta and a count. All right. And then let's take a look at the constructor. The constructor of the counter, so you see its counter has the same name as the class and it doesn't return a type. So that's the constructor. And so we have int cost equals 1. Now, you guys know, have we talked about this? What is this cost equals 1? How can you say equals 1 in the formal parameter? What does that mean? You know what that is? Yes, good. That's a default. It's a default value. So what that means is that if you call the constructor and you leave out the parameter, it will be as if you gave it a 1 for count. All right? And so what does so what does it do? It initializes, here's this, I think this might be a new C++ feature that you might not have seen before. What in the world is this delta parentheses cost and this count parentheses 0? I think this is the first time we've seen this. It is. In fact, delta parentheses cost is equivalent to what? Yes. Have you seen this before? Maybe. All right, so look, actually this is so important, let me write it out because we're going to be doing this over and over again. And then this isn't a semicolon, this is a comma. And then underscore count, parentheses 0, and then we open the brace here, and then we close the brace here. Okay? This, all of this here, including this colon, this whole thing has a name. In C++, this is called an initializer list. And it's kind of weird because what happens is if you put the colon here, then you postpone where the brace starts and where the brace ends. So this is called an initializer list. And it is equivalent to, here's what it's equivalent to. It is equivalent to this. Counter, int, cost gets 1, open brace, and then underscore delta gets cost, this is an underscore, and underscore count gets 0, and then close the brace. Oops, wrong way. Okay, so it's equivalent to this. All right? So that's called an initializer list. So what's the obvious question?
Why?
Yeah, why? Yeah, why do it this way? I mean, you could do it this way. What's the difference? Okay, now, and that is the obvious question. So now here, let me tell you this. Sometimes it is necessary to do it this way. All right. Sometimes, under some circumstances, under some very special circumstances, you cannot do it this way. You have to do it this way. Are you with me? And we are not going to. We're going to see in some of our code later in the course. We are going to see some instances, and we will be able to understand then why you have to do it this way. Because there are some situations where you have to do it this way. You cannot do it this way. So let me just say this now. Rather than try to figure out whether you can do it this way or you have to do it this way, what would be easier? What's going to be easier for us to do? Always do it this way, because sometimes you have to and sometimes you don't. And it's easier just to always do it this way. Are you with me? So it'll be a little complicated when we get to it. When we get to those cases where you have to do it this way. So starting right now, let's always do it this way instead of this way. When we have, and this is called an initializer list in C++. So it's a little mysterious yet because I can't explain exactly when you have to do it that way, but we'll see in the future when you do. Okay? And now here we have a method called getCount, and what does getCount do? Returns the count. All right, so obviously our program uses getCount when our main program used getCount when it did the count. All right. So now here's the next important one. Update. So it's voids, and it's void method. So you call it. You just say update. And when you say update, what does it do to count? Count. What is this? Plus gets delta. That's the same as what? Count gets count plus delta. And if delta, we're saying in our project, delta is always going to be what? 1. So this is saying what? Count gets count plus 1. Are you with me? So every time when we do update, that updates the counter, adds 1 to the counter. Yeah? And then there's a way to clear the counter. You remember how after it did a sort, it would start over, and so you had to clear the counter. Our main program was able to clear the counter. The count gets 0. And you can set the delta. All right? Now, does everybody understand how that counter works? It's a very simple class, and that was all the code for a counter. Now comes the big idea. This is called Parametric Decoration. And what it's used for is it's used to do the comparison and assignment counts, to take the data on how many assignments and how many comparisons are made. And here's the key idea. What we're going to do is Now, check this out. Our abstract sorter sorted what type? T. And T could be what? Anything. It could be int, it could be double, or it could be any class. Are you with me?
So you could sort counters.
Well, not close but no cigar. You can't sort counters, but you can use counters in something to sort. All right? So here's what we're going to do. The name of the class is going to be called CA Metrics. Now, why do you suppose we call it CA Metrics? CA is what? Comparison Assignment Metric. All right? So we're going to write a new class called CA Metrics. And instead of sorting doubles, what we are going to do is we're going to sort objects that have class CA Metrics. Do you see what I mean? So we're sorting objects now. We're not sorting doubles, we're sorting objects. And why are we sorting objects? Because we don't want to just sort doubles. We want to sort doubles, but as we are sorting the doubles, what do we want to have happen? We want to have these counters increment. So the counter is inside the class that we're sorting. Are you with me? The counter is inside the class. So we're not actually sorting the counters, but we're sorting objects of a class, and that class has the counter in it. Do you see what I mean? And so that T in our abstract sorter, that T is going to be a CA metric. This is very clever. Okay? So here's what we're going to do. In CA metrics, we set up two counters, one to count the number of comparisons and one to count the number of assignments. And then what we're going to do is, how do you compare two objects of type CA metrics? Well, what we'll do is we are going to overload the comparison operators so that we can compare two objects of type CA metric, and as a side effect, increment the counter. And we are also going to overload the assignment operator. So whenever we assign to an object of type CA metrics, not only will it do the assignment, as a side effect it will do what? Update the assignment counter. And your program works with no modification of the code. We can use this on your, because it's type T, it's C++ template type. It'll work. It knows no difference, because when it does the comparison, it'll just do the comparison that we define of this. Do you see the idea? Now we're not sorting doubles, we are sorting objects of type CA metric. And the CA metric class has the counter in it. All right? So now let's take a look at the CA metrics class. Now you understand, now this class CA metrics is objects that have this class that's the type that we're going to be sorting. Yeah? So let's take a look at CA metrics. Now here comes another important C++ point. All right, I have to ask this. What are the 3 goals of this course? What are they? The first one is data structures, object-oriented design, C++ code. This is a C++ deal. This one we're going to use, you need to know this really well. What is the meaning of static here when it says static counter underscore compare count? Now you understand that capital C counter, that is the counter class that we just looked at. Are you with me? That has those methods in it. And underscore compare count, that's just the attribute of our CA, one of the attributes of our CA metric. Now, what I want to know is, what does that static mean?
You can't change it at runtime.
Good, close but no cigar.
Can't.
Okay, that's it. Okay, so here's the meaning of static. Remember this always. This comes up all the time. Static means one per class instead of one per object. this is really important. It means one per class instead of one per object. So, you see, here's the thing. Suppose we're sorting, when we sorted 50 numbers, remember when we did the demo and we sorted 50 numbers? Did we want there to be 50 counters? No, we only want there to be one counter for the whole class. We didn't want to have each object have its own counter in it. Do you see what we're doing? We are sorting objects. Are you with me? We are sorting objects, and we don't want there to be a counter. We don't want there to be a counter for, a sub 0 and a counter for a sub 1 and another counter for a sub 2. We want there to be one counter for the whole class that each one of those objects can access. So instead of each one of those objects accessing their own private counter, they are accessing what? The one counter for the whole class. Now, does this make sense? Is everybody clear on this? This is a really big feature of C++ that is super valuable here for us to be able to use. So what do we have? We have one counter for the whole class, and that counter called compare count is the counter to add up the number of times a comparison is made. And then another one called assign count that adds up how many times an assignment is made all right? So there's the two counters. And now, what's the third attribute? What's the third attribute?
T.
Yeah, and what is this capital T? That capital T is the what? That's the type. So there's the double. So see, that T could be double, and then underscore data. So each one of these objects has what in it? It has a double. So we are not sorting doubles, but we are sorting objects, and each one of those objects has a double in it. Do you see what I'm saying?
And why are we doing that?
And the reason we're doing that is so that whenever our program that is sorting these objects does a comparison, our class will not only do the comparison, it will set the counter.
Objects in order to set the...
Good question. Because if we didn't do that, you would have to go in and modify your code to set up the counter in your sorter. You see? Otherwise, how could...
Right.
So what this does, that's a very good question. We need to get this. What this does is this allows us to use your code unmodified and count and do the counts, do statement execution counts in your program unmodified. That's huge. This is do you see what I mean? You don't have
like me having to go add it
and you
in a loop being like
plus compare count exactly, and then you'd mess up. You could mess up your code, whatever.
Yeah. Okay.
Yeah. See how neat that is?
It's neat.
Yeah, it's cool. All right. So those are the three attributes: a static counter for the comparison counts, a static counter for the assignment counts, and then the data. It's a little, one little attribute for each object that stores the data, that stores that value. All right. So now look here in Figure 4.31, continuing. So look. So now these are public. Now we have a. You see that 2t, 1, third or fourth, one. See 2t. What that does is that, in case we ever need to know what the value, the data part of an object is, this will return that value. Okay. And then set t is a way, if we need to set the value of what's inside that little object, then we use set t. So one of them retrieves the value of the underscore data, and the other one sets the value of the underscore data. And then we have a whole list. Now what do we have here? Operator less than or equal to, operator equals equals, operator not equal to, operator greater than or equal to, operator. You see what we're saying? And now what are we doing here? We did this operator. This is operator overloading, right? So what we're doing here is we are saying, okay, suppose we say this. Suppose we say if A sub child is less than A sub child plus 1, something like this. Suppose we have some code like this. What's the compiler going to do? It's going to say, aha, you want to do less than. And it's going to look at what the type is. Now, is the type of A sub child an int? Yes or no? Is the type of A, for our code using this system, is the type of A sub child an int? No. Is it of type double? No, so it can't use double. So what will it look for? So what will it look? It'll see the A sub child is what type? Not T. Not T. CA-metric. It'll look and see, oh, it'll say, oh, this is I'm comparing a CA metric with another CA metric. How am I supposed to do that? And then what will it do? It'll come down here, and if you include this, it'll see what? It'll see this less than. It'll say, oh, operator less than. This is what it calls to do that comparison. Are you with me? And then what's the code for that? Check this out. So here, later on in the figure, I'm jumping ahead because I can't wait. So look, so here's the operator less than. You see the operator less than? So what the compiler does is it calls this code. Now what does this code do? It does underscore compare count dot update. It adds one to the comparison. Are you with me? And then does what? Returns what? What does it return? A Boolean. And what? And how does it calculate the Boolean? What's the Boolean? Underscore what? Data. So now what's that? That is the double that's inside that object. And then is less than what? And the right hand side, so this is the left hand side and this is the right hand side. Are you with me? So is less than what? The right hand side dot underscore data. So it takes the data part of this object and the data part of this object, and then compares them, and it returns either true or false depending on whether it is. So here it's doing it's returning what we expect it to return. Are you with me? But as a side effect, what's it doing? Updating the count. And your program is none the wiser because your program works for type T in general. Now, is that slick?
It's so slick.
All right. Well, anyway, I think it is, and we'll end on that.